So one of the overarching themes of this course, Calculus 2, has been the fact that infinity can lead to surprising results, and you need to be particularly careful when dealing with things that are infinite. Sometimes we'll find that the methods that we have applied without thinking to finite collections of things don't really work all that well once you're dealing with an infinite number of different things. And similarly, sometimes the intuition that we develop working with the finite does not really give us the right answers or does not make a lot of sense when you're dealing with infinity. And we've seen some glimpses of this. For example, we looked at the integral from -1 to 1 of 1 over x squared dx. And we saw that when you try to apply the fundamental theorem of calculus, you get a negative answer, something like -2. And that's not right. So infinite values of our functions cause the integral, the methods of integration that we were used to using, not to work. Okay, so that was one example. Another example is we looked at this curve, 1 over x. And this is the very beginning of the semester when we considered what happens when you rotate that around the x-axis. And we called that Gabriel's horn. That's the name for it. And you can show that this three-dimensional object made by rotating that curve around has the peculiar property that the volume of it is finite, but the surface area is infinite. As if to say that you could fill it with a finite amount of paint, but you could never have enough paint to paint the inside surface, which is very, very counterintuitive. So what I want to emphasize in this video is that infinite series are no different. You can have very surprising and unexpected results that, well, don't make a lot of sense if you're careless with infinity when dealing with series. So we're going to look at a couple examples of things you should not do, but you might try carelessly with divergent series, and then we'll look at conditionally convergent series as well. All right, so to start, let's look at an example. Let's look at the series that goes 1 minus 1 plus 1 minus 1 plus 1 minus 1. And it continues on forever. Now, we've actually argued that this is a divergent series before. Okay, you can apply the nth term test. It is divergent, so it does not make sense to assign any finite value to it. But let's suppose that naively, we wanted to try to apply some of our basic algebra rules to simplify this. Now, one of the things you can do with algebra is when you have a sum, you can always rearrange things, add parentheses as much as you want. And so you can use those sorts of rearrangements to simplify things. And so what I want to do is I want to think about this. Let's put some parentheses in there. Let's group the consecutive pairs of terms. So we can have that as 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. And notice that the expressions in parentheses are all 0. And so based on that, we should probably conclude that the answer is 0, right? Well, maybe not. We said it's divergent, so we kind of know there's something wrong there. But let me change that statement just a little bit. All right, so let's look at putting the parentheses in a different way. 1. Now I'm going to put the parentheses before the next term, so minus 1 plus 1. So that'll take into account terms 2 and 3. And then I'll do plus minus 1 plus 1. So that I'll take into account terms 4 and 5, plus minus 1 plus 1, and so on. So notice I'm still adding up the exact same things. All I did was just put some parentheses to change the order in which I think about the operations. And now notice we've got 1 plus 0 plus 0 plus 0. So obviously that should add up to 1, right? Wait. We just made two arguments that both seem completely valid, and yet we got contradictory answers. We got 0 and we got 1. Well, it can't be both. So clearly something has gone wrong. And in fact, we can even come up with another argument that seems plausible at first glance. Let's think about the sum 1 minus 1 plus 1 minus 1 plus 1 minus 1. And then down below, I'm going to write that sum in a slightly different way. I'm going to put a 0 first. And then I'll just add all the other terms. Okay? And now, let's add those two things together. All right, so s was the thing that we wanted. We have, if we add the left-hand sides, we'll get 2s. And now we'll add these infinite series, 1, minus 1, and so on. And notice, we'll add the first two, we'll get 1. And then we'll add the next two, minus 1 plus 1. And so those are going to add up to 0. And then the next one will add up to 0. And the next one will add up to 0. And that'll go on forever. And so what we've got is, well, just 1. And if 2s is equal to 1, then what is s equal to? 1/2. So now we've just proven that s is both equal to 0, 1, and 1/2. Well, again, clearly something is wrong. And the problem is that we assumed that it was okay to just do things in a different order. By putting parentheses in, you're shifting the order in which you're adding things up. And the result is, well, you get nonsense. So it turns out that's not actually okay. You cannot rearrange terms in a divergent series. You cannot put parentheses in arbitrarily. If it's divergent, it's divergent. We can't do anything else to simplify it at that point. And if you do, you can end up with nonsensical answers like this. All right, so divergent series seem to be a little bit pathological. This is just one of many, many examples that are out there. But I want you to recognize is that infinity takes care. And conditionally convergent series are going to suffer from some problems as well. All right, so let's think about the series 1 minus 1/2 plus 1/3 minus a fourth plus 1/5 minus a 6th, and so on. Okay? All right, and that's the sum of minus 1 to the n plus 1 all over n. Okay, and we show that that is conditionally convergent. And I'm just going to warn you, things are going to get a little bit weird. And the reason for this is that we're assuming we can do things that we shouldn't be able to do. So there's a flaw in this argument. Just keep in mind that when you get weird answers, that's because we made a faulty assumption. All right, so here's what I want you to notice. I want you to notice, first of all, that if you look at all of the terms with an odd denominator, they have a plus sign, right? 1 over 1, 1 over 3, 1 over 5, they all have plus signs. And so we could imagine thinking about this if we were to rearrange things as 1 plus 1/3 plus 1/5 plus 1/7, and so on. And then all of the even terms have negative signs. And so we could have 1/2 plus 1/4 plus 1/6 plus 1/8 plus 1/10, and so on. All right. Now already I'm rearranging the order of the terms, which should be a red flag. We have no basis for knowing that that's actually something that we can do. But if we were able to do that, you'd notice that when you look at the odd terms, we could write this as the sum of 1 over, if you want to get only the odd powers, if you make the denominator 2n minus 1, you'll see that that actually works up. So you can plug in 1, you'll get 1 over 2 minus 1, so 1 over 1. If you plug in 2, you'll get 1 over 2 times 2 minus 1, which is 3. And so that will take into account all of those. And for the other one, notice you could factor out a 1/2. And that would be, let's see, that would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, and so on. Which means we could write this as 1/2 times the sum of 1 over n. And you can show that both of those two series are divergent, right? The one on the right, 1 over n, we've dealt with a million times. the first one, 1 over 2n minus 1, is a little bit trickier, but basically it's going to behave like 1 over n, and you can use a comparison test to show that. Okay, so both of those are a divergent series, and what that means is we have enough odd denominator terms to go off to infinity, and we have enough even denominator terms to go off to negative infinity, since they have a minus sign. So that's a little bit interesting. Now, I claimed in a previous video, without proving this, that the sum is actually convergent, and it converges to log 2. And that is indeed correct. That does converge. This is a conditionally convergent series, and when you have the alternating, it actually does converge to that value. But I want you to notice something, is that once we start rearranging the terms, things get strange. Okay? All right? So let's look at this. I'm going to just write all the terms in the sum in a different order. I'm going to start with 1, and then I'm going to subtract even-powered terms until I get something that's negative. Okay, so I'll subtract a half. Well, now I'm still at 1 positive 1/2. I'll subtract a quarter. And then I'll subtract a sixth. And a sixth is not quite as big as a quarter, and so I'm still positive, but if I subtract an eighth, you can check this, but 1/6 is bigger than an eighth. So here it's like negative 2/8, but a little more. Well, 2/8 is a quarter. If you take a quarter and another quarter, you get a half. And you take a half and a half, you get 1. And so this is all just a little bit bigger than 1, of course, with a negative sign. And so this is going to be less than 0. All right. Now, if I were to just stop there, obviously I wouldn't be done. So I need to include all the other terms. And so now I'm gonna take into account another odd term. And the first odd term would be 1/3. And then the claim is I can find enough even terms to subtract off to make this negative as well. So I'll subtract a 10th. I'll subtract a 12th, 14th, and a 16th, and an 18th. And at that point, you can check, actually compute the fractions, but that's definitely going to be negative. And I know for a fact that I can do this because remember, I have enough even denominator terms to create a divergent series, right? I have an infinite number of even number terms, and the sum of those even denominator terms is infinite. And so I can definitely choose enough terms to make that negative. And then, well, I want to make sure, again, I'm including all the terms in the series, and so then I'll put a 1/5. But then I'll subtract off some more even terms. And then I'll do the same thing with 1/7. And then I'll subtract some more even terms. And you'll notice that if I continue this process forever, every single odd term will eventually be accounted for, right? Each of those parentheses has one of our odd terms. And so if we continue forever, there will be a parentheses for 191st, 193rd, and every odd number denominator. And similarly, every even number term will be accounted for. Negative 1/2, negative 1/4, negative 1/6, negative 1/8. So I got the first 4 in that first parentheses. I've got the next 5 in the next parentheses, and I'll have a bunch in the third and the fourth and so on. So every single fraction is accounted for, and they're only included once. Which what that means is this sum that I've written has exactly the same terms in it as the original series, which we said converged to ln of 2. But what's the problem? Well, notice every term in parentheses is negative. And if you add up a bunch of negative numbers, can you get something positive? Well, of course not, right? You add up a bunch of negative numbers, you get something negative. And so what that means is this sum must be less than 0. If you rearrange the terms, we get a negative answer. But how can that be? How can you take something that converges to log 2, rearrange the order, and get something negative? Well, the answer is you cannot rearrange the terms. Rearranging the terms of a conditionally convergent series changes the answer. And in fact, I made this argument to show that you could get something negative, but if we ordered the terms in a different way, We could get a conditionally convergent series that converges to any number that we want. You want to make them add up to pi? Well, here's what you do. You start with the positive numbers, 1 plus 1/3 plus 1/5 plus 1/7. You go on until you get bigger than pi. Then you start adding negative terms until you get below pi. Once you get below pi, you start adding positive terms until you go above. And then once you go above, you start adding negative terms until you go below. By alternating back and forth like that, just like we did with any other alternating series, what you can do is guarantee that you're going to converge to pi or e or any number that you want. So let me write that down. If you rearrange the terms in a conditionally convergent series, then you can change the answer. So order matters, and you can make the sum add up to whatever you want. Now, I don't know about you, but I find that remarkable. It just seems so mind-blowing that you could add the same numbers just in a different order and somehow get them to add up to any particular number that you would like. And yet, that's exactly what we've just argued, and you can prove that this is indeed correct. So, what's the takeaway message? Well, I think there are a couple of them. 1, be careful with infinity. 2, don't just rearrange the terms in an infinite series. Unless it converges absolutely, you have to be that could potentially change the answer. And 3, sometimes math is full of surprises. Infinity in particular, it's very hard to wrap your mind around that the fact that this could be possible because it's so ingrained in us that when we add things up or subtract them, the order doesn't matter. And yet here we have an example where the order does indeed matter. It changes the answer. And so I hope you appreciate that fact and just how surprising it is, and also how cool it is that conditionally convergent series can do such unexpected things. All right, so some of you may be wondering, is this going to be on the exam? And I saved this for the end of the video, but the answer is no. Rearrangements of conditionally convergent series is not something that you're going to be tested on, but I do think it is an important or interesting fact that's worth sharing. And so I would encourage you and your friends to watch the video to get an understanding for this, so that you have that story in the back of your mind to remind you to be careful with infinite series.